Welcome to Chapter 6. This is the last chapter that we will cover in this class. This video will cover section 6.1, inner product length and orthogonality. In this chapter, in order to find an approximate solution to an inconsistent system of equations, we need to come up with a well-defined notion of nearness because there isn't an actual solution. So in this section, we are going to come up with some geometric concepts of length, distance, and perpendicularity. And these ideas are well known in R2 and R3 spaces, but in this section we'll define them for Rn. And this will help us solve different applied problems, like least squares problem. And in order to do this, we need the inner product of two vectors in order to do this. So that is going to be one of our primary focuses in this section. So, as mentioned, we're going to consider a way to multiply two vectors in the space Rn, and this idea is going to be extended to more general vector spaces. Remember, we can transpose a vector. So that is needed in the definition of an inner product. So the number u transpose v is called the inner product of u and v, and it is denoted in either this way or this way. And it's often referred to as the dot product as well. And so this is read u dot v. So since this is referred to as the dot product, then what we can do is recall that u transpose v is the same as u dot v. So if I transpose u, then I will have u1, u2, un, and v is v1, v2, vn. And so the dot product is just taking this times this, plus this times this, plus this times this, so on and so forth. And that's what we have. So these are vectors in Rn, and this is the inner product, also known as the dot product. So let's look at an example. So we are asked to find two things here. So let's start with u dot v. Recall that u dot v is the same thing as saying u transpose v. So if I transpose u, I have this here, and v is this. So if I multiply these two vectors, then I end up with 4 times -2 plus 2 times 5 plus 3 times 6. And this gives me 20. On the other hand, if I want to find v dot u, well, this is the same thing as v transpose times u. So v transpose is this here, and here is u. So if I multiply these two vectors, then I have -2 times 4 plus 5 times 2 plus 6 times 3, and this also equals 20. We will find that these dot products are commutative, and the inner product holds true for both of these. These are equivalent. Go ahead and pause this and see if you can find the inner product of these two vectors. So again, u dot v is going to be equivalent to v dot u, which is the same thing as u transpose v. In this case here, you should find that this is equal to -1. So here is our first theorem in this section, which can be found on page 333. Here, this talks about the commutativity, that's hard to say, try it, of these two vectors in Rn. These two parts here can be combined so that we can have a large statement or a combination of the two. And then u dot u is equal to 0 if and only if u is equal to 0, or if you have that 0 vector. Sometimes we will want to find the length of a vector, which is denoted in this way here. Sometimes we refer to it as the norm of the vector as well. And it is defined in this way here. So this definition also states that this is equal to v dot v. Okay, so really there are a couple different ways you can find this length. Typically I use this definition just to keep consistent. So if I want to find the length of this vector here, so this vector's in 3 space, and we want to find this length, the definition says to take 4 squared plus 2 squared plus 3 squared, and then take the square root of that sum. So 16 plus 4 plus 9 gives me the square root of 29. That cannot be simplified, so the length of vector u is root 29. If we have a vector of length 1, this is known as the unit vector. And if we divide a vector by its length, then we obtain the unit vector because of this. Sometimes it's called normalizing, but really what we want to do is identify if we have a vector of length 1 or not. So here it says let v be this vector, and we want to find a unit vector. So remember, a unit vector is length 1 in the same direction as v. So I can draw this vector in 3 space. Okay, so if I wanted to draw this vector, I could. And it has a specific direction, and I want this unit vector to be the same direction as this. So the first thing I want to do is I want to find length v, the length of vector v. So when I do this, just like we did in the previous examples, I'm going to take 4/3 squared plus -1 squared plus 2/3 squared. So squaring each of these, I have 16/9 plus, I'm going to have a denominator of 9, so I'm going to, instead of writing +1, I'm going to write it as +9/9 plus 4/9. I have a common denominator of 9. The sum of the numerators is 29. So I can take the square root of the top over the square root of the bottom, and this results in a length of the square root of 29 thirds. Okay, now that's not my answer. If I want to find a unit vector, what I need to do to find u is take v times 1 over the length, as stated in the previous slide. So v times 1 over the length, this here is the same as taking the reciprocal of this. Okay, so I'm going to multiply by 3 over the square root of 29. So I'm just going to basically multiply each item by 3 over root 29. And when I do, in this first one, the 3's cancel, so I'm left with 4 over root 29. Then negative 3 over root 29, and again the 3's cancel, so 2 over root 29. So this is a unit vector in the same direction as v. Now, so this is my answer, but there is a way to verify this. So if we want, we can verify that the length of u is equal to 1. And in order to do that, this here is u, vector u. So I can plug that into the same formula that I did here. So I'll have the square root of 4 over root 29 squared plus negative 3 over root 29 squared plus 2 over root 29 squared. This results in the square root of 16 29ths plus 9 29ths plus 4 29ths. This equals the square root of 29 29ths, which is the square root of 1, which is 1. So that verifies that this vector is indeed a unit vector because it has length 1. We know it's in the same direction as v because we used v here. Sometimes we will want to find the distance between two vectors, u and v. For example, I might have this as vector u, maybe this is vector v, and I'll want to find the distance between the two, which is sometimes referred to as theta. So if I want to find that distance, then I will take vector u minus vector v and find that length. And that kind of goes back to the parallelogram rule that we studied early on. So here, if I want to find the distance between these two vectors, and remember, these vectors are in 2 space, so we can sketch them in. 7, 1 is like this vector here, and vector 3, 2, so this would be the point 7, 1. And then vector u, the point 3, 2, would maybe be this here. So we would want to find this distance between the two. Okay, so to do that, the first thing I want to do is subtract the two vectors. So vector 7, 1 and 3, 2. When I subtract these, I get a new vector of 4, negative 1. Okay, well, if I find the length of that, using the same formula that we used on the previous slides, we end up with the square root of 16 plus 1, which is 17. So the distance between those two vectors is root 17. Another topic that you will see in this section involves orthogonal vectors. So orthogonal vectors occur when the two vectors, the dot product is equal to 0. Orthogonal vectors means that they are perpendicular. So that means if you have this vector, then another vector here, they create a right angle. Okay, so we have this theorem here, which is helpful, but it's not really seen in the homework. But I think you'll find that this homework is pretty straightforward. There's nothing too terribly complicated. So I think you should enjoy it. That's it. Enjoy.